Hi everyone, my name is Frederick Cho, and I'll be presenting on my joint work with Sahil Singla on submodular dominance and its applications. Our focus today is on the class of submodular functions, which are set functions whose formal definition is written here. Intuitively, submodular functions capture the idea of diminishing returns, and thus are very expressive for practical applications. Directly optimizing over an expressive class of discrete functions is generally difficult, so one common technique in submodular optimization is to define a continuous relaxation, where each element, instead of being included or excluded, is assigned a fractional value between 0 and 1. This allows for the use of efficient techniques from continuous optimization. Such techniques have given us optimal polytime algorithms for submodular maximization and optimal additivity gaps for stochastic probing, to name a few results. One way of interpreting continuous relaxations is as a distribution. For example, the multilinear extension F is defined as the expectation of f over the product distribution with marginal probabilities given by the vector x. As the multilinear extension sees wide use in maximization applications, we are interested in what kinds of distributions match the value of the multilinear extension. In particular, we say that a distribution D with marginals x satisfies submodular dominance precisely if the expectation of f over D is at least capital F of x. Recall that submodular functions capture the idea of diminishing returns. Then any positive correlations can only decrease the expectation of a submodular function. And so we turn our search for distributions that satisfy submodular dominance to negatively dependent distributions. The main questions we ask are, can we characterize the relationship between negative dependence and submodular dominance? And having done that, how can this characterization be applied in submodular optimization? First, we will define some notions of negatively dependent distributions. The first is negative cylinder dependence, or NCD, which can be thought of as pairwise negative correlation, but for any subset of elements rather than just pairs. Note that this condition written here also applies with the indicators for I and S, all substituted for indicators for I not in S. The second is a notion that we introduce, called weak negative regression, or WNR, which means that the expectation of any monotone non-decreasing set function not depending on element I decreases when conditioning on the inclusion of I. This can be equivalently stated in terms of covariances as written here. This is a graphic summarizing our main results. We show that submodular dominance sits strictly between NCD and WNR. That is, WNR implies submodular dominance, which in turn implies NCD. Additionally, we show that negative association and negative regression both imply WNR, making a useful generalization of two popular notions of negative dependence. This is nice for the hierarchy of negative dependence, as the exact relationship between negative association and negative regression is not known. Now, we'll go over a quick proof outline of these containment results. First, we show that WNR implies submodular dominance. We prove by induction on the number of elements. So let f be any submodular function, d be a WNR distribution with marginals x, and let d sub k be the same as d, except element k is sampled independently. To prove the theorem, we can show this chain of inequalities, that the expectation of f over d is at least the expectation of f over d sub k is at least the expectation of f over the product distribution with marginals x. The second inequality follows by the induction hypothesis, as k is sampled independently in both expectations, and so the conditional distributions on k have the same marginals and have one fewer element. The first inequality can be rewritten as this inequality down here. This f of s union k minus f of s set minus k expression is called the contraction of f on k. And a property of submodular functions is that the contraction is always a non-increasing function. So this inequality is implied directly by the WNR condition and flipping the signs. which finishes this part of the proof. Next, we show that submodular dominance implies NCD. The main observation is that this negated product of indicators is submodular. The easiest way to see this is by embedding it in a uniform matroid rank function and using the fact that all matroid rank functions are submodular, but the details aren't so important. After showing this negated product of indicators is submodular, substituting it into the definition of submodular dominance and flipping the signs yields the NCD condition. The same technique works for showing that the product of indicators of I not an S is submodular, and this similarly yields the other condition for NCD. Finally, here are two examples which show that neither containment is tight, meaning that WNR is not equivalent to submodular dominance, which is not equivalent to NCD. Both the distributions listed here are uniform over their supports. The first distribution is not WNR, because conditioning on the inclusion of element 3 increases the probability that either element 1 or element 2 is included. On the other hand, by inducting on element 2, as in the proof of theorem 1, the first distribution can be verified to satisfy submodular dominance. The second distribution does not satisfy submodular dominance, because the rank 2 uniform matroid rank function has higher expectation under the product distribution with the same marginals. On the other hand, it can be directly verified by the NCD condition that the second distribution is NCD. Now, we'll turn towards a handful of applications of submodular dominance relating to rounding. As previously mentioned, a common method of submodular optimization is to optimize over the multilinear extension using tools from continuous optimization. The problem is that since the multilinear extension is a continuous relaxation, we may end up with a fractional solution when we want an integral solution to the original problem. Converting from fractional to integral solution is a process known as rounding. Ideally, we don't want to lose any value during the rounding process, as this will cause our approximation ratio to suffer. Then, because a fractional solution for the multilinear extension corresponds exactly to the expectation over a product distribution, the simplest way to achieve this is to sample an integral solution from the product distribution with marginals equal to the fractional solution. However, sampling this way may not yield a valid solution if there is a feasibility constraint. Instead, we can sample from a WNR distribution over the feasibility constraint, and submodular dominance ensures that the resulting distribution of solutions is at least as good in expectation as that given by the product distribution with the same marginals. Contention resolution schemes, or CRSs, are another rounding technique, the details of which are not important here. A prior result reduced the existence of optimal CRSs over matroids for distribution D to whether D satisfies submodular dominance. Therefore, our result shows that optimal CRSs over matroids exist for any WNR distribution. Previously, CRSs have primarily been studied only for product distributions. One more concrete application is in a problem known as the submodular profit inequality. Similar to the classical profit inequality, we have a sequence of items, which are independent random variables, with known distributions presented one by one in adversarial order. The difference is that here, the items are discrete random variables, whose images form a set of elements, and the goal is to select items subject to a packing constraint, such as a matroid, as to maximize a submodular objective function on the elements. One thing to notice is that even though the items themselves are independent, the elements do not form a product distribution, which is problematic when we want to analyze the value of the objective function. Prior approaches to this problem optimize offline using the multilinear extension and round using an online contention resolution scheme, or OCRS. However, because we only know of OCRSs for product distributions, the prior analyses lose additional factors to mask the distribution of elements as a product distribution. In our case, since the elements form a WNR distribution, we are able to modify the analysis of the OCRS to work directly on the elements, and so we are able to achieve optimal competitive ratios whenever optimal OCRSs are known. This summarizes our main results. The main open question is whether we can find an exact characterization of submodular dominance in terms of negative dependence. As recall that the class of distributions satisfying submodular dominance sits strictly between those satisfying NCD and WNR. Another promising direction is designing explicit methods to sample from WNR distributions for various set families, as this would result in concrete rounding techniques. Aside from these, it would be interesting to look at what kinds of distributions can get close to the expectations of product distributions. For example, we know that NCD is not enough for submodular dominance, but is it enough to get a 1/2 approximation of the multilinear extension? Related to this, can we extend some notion of approximate submodular dominance to the class of XOS functions, which contains the class of submodular functions? Finally, since we know that negatively dependent distributions behave favorably in expectation on submodular functions, it would be interesting to show whether the same strong concentration we observe in product distributions for submodular functions also holds for certain classes of negatively dependent distributions. That's it for this presentation. Thank you for listening.